Well, thanks for joining me. Today we're going to be talking about how to find percent composition as well as how to work with an empirical and molecular formula and explain the difference between those two. So let's begin. So if I were to take magnesium, and here's this block from the periodic table, and chlorine, and here's this block from the periodic table, I could make a compound from these. Now, perhaps you remember magnesium is an alkaline earth metal, so it has a +2 charge, and chloride is a halogen, so it's a -1. And so these would get together and they would form the compound MgCl2, magnesium chloride. Now, if I were to ask what is the percent magnesium in magnesium chloride, most students would tell me 33% because 1 out of the 3 is magnesium. Well, it turns out it's not 33 1/3%, all right? And chlorine's not 66.7%, right? So what's going on here? Well, this little manhole cover is open and we don't want to fall in that hole. And this is the hole I'm talking about. So instead, what we have to understand is percent composition is always by mass, not atoms. So this was by atoms when we said 33%, and we want it to be by mass. So let's go ahead and see how that might look. I think you would agree with me that magnesium chloride contains 1 magnesium and 2 chlorine atoms. The molar mass of magnesium is 24.305 grams per mole. The molar mass of chlorine is 35.453 AMU, or excuse me, grams if we're doing molar mass, AMU if it's a single atom. Well, I'll figure the atomic mass here. So we have 1 magnesium, that's what the formula says, and it weighs 24.3. And then I have 2 Cl's, and they each weigh 35.5. 2 times 35.5, I add these two numbers up, and I get the mass of this compound. And that mass, as you might expect here, 95.21. Now, if I want to find the percent of something, because it's called percent composition, the percent is defined as the part divided by the whole times 100. For instance, if you had a quiz and there were 10 questions and you got 8 correct, you'd have 8 divided by 10 is 0.8 times 100, that's an 80%. So if I want to find the percent that's magnesium, well, 24 grams of it is magnesium out of the total 95. That comes out to 25.5% magnesium, and of course the 2% have to add up to 100, so the remainder must be 74.48% chlorine. Okay? All right, that's what I mean by percent composition. It's always by mass. Now, let's talk a little bit about compounds, empirical and molecular. I'm going to go ahead and I'm just going to get rid of this completely, I think, and I'm going to switch to a pen so I can write on here and maybe explain stuff a little bit better to you. Okay, you don't need to see my face. All right, so an empirical formula is the reduced form of a compound. The molecular formula is what you find in nature. So for example, I could have N2O4, that's dinitrogen tetroxide, and that would reduce to the empirical formula of NO2. That would be its empirical formula. So an empirical formula is the lowest ratio of the molecular formula. They could be the same, but they're going to be the difference between empirical and molecular. You'll have some factor, either 1 time, 2 times, 3 times bigger, 4 times bigger, some whole number factor bigger. The empirical formula is figured experimentally in the lab. And then with a little bit additional information, we can figure out the molecular formula. And I'm going to demonstrate both of those to you. So the statement reads, a pure compound, and molecules and compounds are pure substances, always consist of the same elements combined in the same proportions by weight. That's important that they're always going to be the same composition. So therefore, we can express molecular composition as a percent by weight. And that's what we're talking about. So for instance, here's ethanol. This is grain alcohol. It has the formula C2H6O. And I have these percentages by weight. How did we get those? Well, If you have a periodic table in front of you, it might be easier. This formula says we have 2 carbons and they each weigh 12 grams per mole. That's 24 grams. We have 6 hydrogens. Each hydrogen weighs 1 gram per mole. And finally, I have 1 oxygen and it weighs 16 grams per mole. So if you add all this up, you get 46 grams for what's called the molar mass of ethanol. Now, the percent that is carbon, I can do that up here, the percent that's carbon is the part that's carbon, 24 grams, divided by the whole, 46 grams, then times 100 at a percent. Well, that comes out to be 52.13%. And I could do the same thing for the percent that is hydrogen. It's equal to the amount that's hydrogen, 6 grams, divided by the whole, 46 grams, times 100, and that would come out to be 13.15%. And finally, if I simply took 100 and subtracted the first 2 percentages, I would figure out the last percent, that amount which is oxygen. All right, so let's now try an example of an empirical formula question. So it says quantitative analysis. That means numbers are involved. Shows that this compound contains sodium, sulfur, and oxygen, and the percentages of each are shown. So here's what we do. To find the empirical formula, we're going to follow 3 very simple steps. The first step is change percent into grams. Now, what does that mean? Well, we could have any size sample we want. It could be 2 grams, it could be 100 grams, it could be 17 tons. I'm going to keep my life simple and assume that I have a 100-gram sample. So if I have a 100-gram sample, then 32.38% of that would be 32.38 grams. So really, just take the percentages and change them to a gram. Now this works because, as we stated in the earlier example, the mass percent in a compound is always the same because they're pure substances. Next, we don't want to write the formula like, let's do this, Na 32.38 S 22.65 O 44.99, right? A, that looks silly. B, it implies you can get parts of atoms, which is not true. Now, it is true that a formula relates to the mass of the element, but it's actually a mole ratio, okay? It's a mole ratio. So what does that mean? Well, it says step 2, let's convert all the grams from step 1 into moles. Now, to help you with this, you'll probably need a periodic table. Sodium is element 11, and it weighs 23 grams per mole. So I'm simply going to divide 32.38 by 23 grams, because that's the molar mass of sodium. Grams of sodium cancel, and then I get 1.408 moles of sodium. Now I'm going to do the same thing with sulfur. Sulfur is element 16, and it weighs 32 grams per mole. So again, notice the way I have this set up. The grams of sulfur cancel, and I'm left with moles of sulfur. 22.65 divided by 32 is 0.708 moles. And finally, let's do it for the last example. Oxygen is element 8, and it weighs 16 grams per mole. Again, please notice the grams of oxygen cancel, and I'll be left with moles of oxygen. Now, the other thing I want to point out is when I write these values, notice that I keep quite a few decimal places here. I will generally keep 3 or 4 decimal places. Don't round too early. It'll cause problems later on. Now at this point, I'm getting closer. I could write my formula Na 1.408, S 0.708, O 2.812. Now, that's the right ratio of the atoms, but it's not right because it still has, look at that sulfur, 0.708 atoms. So the quick and dirty fix here is our step 3, divide by the smaller number of moles. And in this case, between 1.48 0.708 and 2.812, 0.708 is the smallest number. So divide all three by 0.708. And what you'll get for the first one is 2 sodiums. For the second one, 1 sulfur. And the last one, 4 oxygens. So now we put that information together, 2 sodiums, 1 sulfur, and 4 oxygen, and we get the right empirical formula, Na2SO4. The name of that compound is, of course, sodium sulfate. And that's the basics of how we do an empirical formula. The steps are outlined on the bottom of the slide. Step 1, percent to grams. Step 2, grams to moles. And step 3, divide by the smaller number of moles. Now, of course, there's some other little small things that I'll share with you that'll make it a little bit more complicated, but this is the basics of what we're going to be doing. Let's try another one. A sample weighs 250 grams and is analyzed and found to contain the following elements in these percentages. And our job is to find the empirical formula. Well, first off, this 250 grams, we don't need that information at all. All we need to know is the percentages. Once we know the percentages, it's going to be easier to assume a 100-gram sample and just convert those percentages to grams. So that's what we're going to do. Step 1, convert percent to grams. So I'm going to take all of those amounts and just change them into grams. There we go. And again, this is okay to do because all samples of a compound are a pure substance contain the same percent. If it's a 100-gram sample or 250-gram sample, the same percent. Do you remember what we do next? You got it, convert grams to moles. So let's do that now. So sodium is element 11 on the periodic table, and it weighs 23 grams per mole. Notice that grams of sodium cancels with grams of sodium down here, and I'm left with 1.1904 moles of sodium. Hydrogen weighs 1 gram per mole. Its atomic number is 1. So take 1.19 divided by 1, and you get 1.19 moles. Next, we're going to do carbon. Carbon is element 6. It weighs 12 grams per mole. So notice that I'm dividing by 12 grams per mole, and I get 1.908 moles. And finally, let's do one more. We got oxygen. It's element 8. It weighs 16 grams per mole, and that cancels. And now we're left with 3.5712 moles. The last step, remember, because we don't want to have decimals, is to divide by the smallest number. And the smallest number here is 1.19. So when you divide those by 1.19, you end up with 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens. Now, before you want to start arguing with me about 1.1904, 1.19, 1.908 aren't the same, these are experimental numbers. If you got those in your lab, you would say they're all the same. So what did we make? Well, it spells out nachos, but nachos is really sodium bicarbonate, right? NaHCO3 is sodium bicarbonate, commonly referred to as baking soda. So you see, we can do more than 2 elements with this. We can do 3 or 4, whatever it takes. We can figure out its empirical formula. All right, I'm going to throw you a little curveball on the next one. We have here, it says a 175-gram hydrocarbon is analyzed and found to contain around 83% carbon. Well, let's break this down for a second. The word hydrocarbon means that it contains only the elements hydrogen and carbon. And we're told that we have 83% carbon. Well, the rest then must be hydrogen. So even though it doesn't state it, we understand there's 17% hydrogen. Now, that first line is the only thing we need to get the empirical formula. Once we have the empirical formula, then we're going to use the information in the second line. The molar mass of the sample is 58 grams per mole to get the molecular formula. Okay? Let me show you what I'm talking about here. So the first thing we're going to do is get the empirical formula that we want. So we have to convert percent to grams. Well, we already have the percentages, 17%, 83%. So let's just write them down, assuming a 100-gram sample. Again, remember, the sample size they give us,
we don't need to worry about that. We're just always going to assume a 100-gram sample. So we have 83 grams of carbon, 17 grams of hydrogen. Step 2 in an empirical formula, remember, is to convert grams to moles. So we do this by dividing by the molar mass of each element. Carbon weighs 12 grams per mole, and hydrogen weighs 1 gram per mole. And that's what I'm showing in this step. Notice the grams of carbon cancel, and I'm left with moles of carbon. Grams of hydrogen cancel, and I'm left with moles of hydrogen. Finally, divide each by the smaller number to get a whole number. So I'm going to divide them both by 6.917. And when I do that, it comes out different this time. I got 1 carbon, but on my calculator it says 2.4577. Well, what I'm here to tell you is you're not going to take and write CH 2.5. You're not going to round down and call it CH2, and you certainly aren't going to round up and call it CH3. So what do we do then? Well, how about we keep the ratio CH 2.5 and double everything and get C2H5, okay? Anytime you do step 3 and you get a number that ends with 0.5, I want you to double everything. If you get a 0.33 or a 0.66, you're going to multiply that by 3 to take care of those, okay? So that's going to be the little trick that I was telling you about. There's going to be one coming up that's a little tricky. So when you see that, a 1 and a 2.5, you're going to simply double both and make them C2H5 to keep the ratio. Now, C2H5 is the empirical formula. Now, somehow that formula relates to the molecular formula, and we know the molecular formula weighs 58 grams per mole. So let's take a second to figure out what 2 carbons and 5 hydrogens would weigh, our empirical formula. So 2 carbons each weigh 12 grams is 24, and 5 hydrogens at 1 gram is 5, that's 29 grams. I need this thing not to weigh 29, but to weigh 58. Well, I can kind of see that in my head. 58 divided by 29 is 2. So therefore, I need something twice as big as C2H5, so C4H10 is the molecular formula. Remember, I told you to go from the empirical to molecular. It could be the same number, it could be doubled, it could be tripled, it could be 4 times, it could be any number. In this case, it was doubled to get to the molecular formula. All right, we're about 18 minutes into this. We're doing pretty well. I'm going to do a few more examples, and then I'm going to turn you loose. And if you're wondering, C4H10 is called butane. It's what's in your Zippo lighter. All right, let's talk about mistakes that people make when doing an empirical formula, okay? Let's assume that I have some compound and it contains 36.3 grams of zinc and 17.8 grams of sulfur. Here's what a student might do. They're going to take, to get the empirical formula, they're going to take those masses, they're going to divide by the smaller number, in this case 17.8, and they're going to get a very nice 2 and a 1, and they're going to put it together, and they're going to say Zn2S. Now, the mistake we made here was step 1 was to get grams, step 2 said convert grams to moles, and then step 3 was divide by the smaller numbers. We divided at the wrong time. So that's not right. What we should have done instead, and understand the chemical formula is indicating a mole ratio of the atoms there, not a gram ratio. And so if we would have taken our 36.3 grams of zinc, 17.8 grams of sulfur, zinc's molar mass is 65.4 grams per mole. And so let's go ahead and divide that. 65.4 grams of zinc is 1 mole. Grams of zinc cancel, and I have 0.555 moles of zinc. Well, let's do the same thing for sulfur. Sulfur is element 16, and it weighs 32 grams per mole. Grams of sulfur cancel, and that comes out to also be 0.555 moles of sulfur. Well, that's step 2. Step 3 said divide by the smaller number of moles. In this case, 0.555. Well, if you do that, you get 1 for both of these. You get 1 zinc and 1 sulfur. Putting that together, we get the compound we're looking for, zinc sulfide. Now, if you have just finished a unit on nomenclature, you remember zinc is +2 and sulfur, 2 away from the noble gas argon, is -2. So they should be the formula ZnS, not Zn2s. So please remember that order. The order is step 1, we're going to change percent into grams. Step 2, grams into moles. And finally, step 3, divide by the smaller number of moles. Don't do those out of order. All right, getting near the end here. So let's find the molar mass and percent composition of zinc acetate. Hopefully you remember zinc is always a +2 ion, and I've given you the acetate ion right here. It's not one that I generally have my students memorize. And so there it is. Now, if we want to make this come together, of course, we could do the crisscross rule or use logic and figure out that we must have to have 2 1 negatives to balance that 2 plus. So the formula for zinc acetate is shown here, Zn parentheses CH3COO2. Next, in this formula here, this thing, we have 1 zinc. Then in the parentheses, we have 2 carbons, but there's a 2 outside, meaning we double everything inside. So there's a total of 4 carbons. There's 3 hydrogens in the parentheses, but that gets doubled. So 6 hydrogen. And there's 2 oxygens in the parentheses. That gets doubled, 4 oxygen. So this is zinc acetate. We want to find its molar mass. Well, we know it has 1 zinc. And as we talked about earlier, zinc is 65.4 grams per mole. It has 4 carbons. Carbon weighs 12 grams per mole. It's atomic number 6 on the periodic table. 4 times 12 is 48. Hydrogen weighs just 1 gram per mole, and there's 6 of those. And oxygen, element 8, weighs 16 grams per mole. So that's 64 grams. Adding that all up, we will get the molar mass of the zinc acetate. And there it is, 183.4 grams. So we did the first part, we got the molar mass. Now, if you want to get the percent, please remember percent is the part divided by the whole times 100 at a percent. So in this case, take each one of these masses and divide by the molar mass. 65.4 divided by the total, 183.4 times 100, 35.6% zinc. And you can see I've done all of them the same way. Now, the really neat thing is, once we do that, we can take these percentages and we can work backwards to see if we get our formula. So we can kind of check our own work. I think that's pretty cool. All right, last example here that we'll do together. A compound is found to be 45.5% yttrium, that's element 39, and 54.5% chlorine, that's element 17. And we're given its molar mass is 590 grams. So we want to know 2 things here. Find its empirical formula, and once we do that, use that information to find its molecular formula. So let's see if we can remember what to do. Step 1 was to convert percent into grams. So assuming a 100-gram sample, then we have 45.5 grams of yttrium and 54.5 grams of chlorine. Step 2 says convert grams to moles by dividing by their molar mass. Again, yttrium is atomic number 39, and it weighs 88.9 grams per mole. Grams of yttrium cancel, and we're left with 0.5118 moles of yttrium. Chlorine is element 17. It weighs 35.5 grams per mole. Grams of chlorine cancel, and that gives us 1.535 moles of chlorine. Step 3 said divide both of those moles that you get by the smaller number. Well, the smaller number is 0.5118 moles. That gives me 1Y and 3 CLs. Now, putting that together, that is the empirical formula YCl3. Now, we know that that empirical formula somehow has to relate to the molecular formula. And if you remember what we did last time, we had to calculate the molar mass of YCl3 first. So in YCl3, there's one Y that weighs 88.9 grams and 3 CLs that weigh 35.5. If you add those two numbers up, you get the molar mass of the empirical formula, that's the YCl3, and it is 195.4 grams. Well, that's roughly 200, and we're told that the molecular mass of the molecule is roughly 600. I bet we have to multiply by 3, but let's check it out. 590 divided by 195.4 comes out to be 3. So we're correct. So we want to multiply our empirical formula, YCl3, times 3. And if we do that, we get Y3Cl9. That is the molecular formula, and YCl3 is the empirical formula. And notice that they're related to each other by a factor, a whole number factor of 3 in this case. Sometimes they'll be the same number, other times they will not be. It's just the way that these things go. Okay? All right, I think we are done. So we walked through how to find the percent composition. We noted it's always by mass. Then we learned what an empirical formula is and how to find it. And then finally, if we add or have the additional information of the molar mass of the sample, we can change and go from an empirical formula to a molecular formula. Hope this was helpful. Take care. Bye-bye.